Okay, so what we're going to do now is start our work on Courset's and Lagrange's theorem. It'll probably take up some of next week's lecture as well. And Courset's are important in their own right, but for us, the main reason for looking at them is they're going to help us prove Lagrange's theorem. In fact, once we've developed the theory of Courset's, Lagrange's theorem will be very easy to deduce. But Courset's are used in other contexts as well. I think I've mentioned already that in coding theory cryptography, Courset's are used. So those of you who are doing coding theory module might have seen some Courset's lurking. Have you seen any Courset's lurking in the cryptography coding module? Usually, I think perhaps towards the end of the module you may see some. And you may have seen Courset's in linear algebra last year and not called them Courset's. So Courset's are important in any case, but for us we're going to use them to deduce Lagrange's theorem. And so a quick advert for Lagrange's theorem. In fact, let me state Lagrange's theorem now, and we're going to work towards a proof over the next week or two. So this is the same Lagrange you may have met in other contexts. So this is the same Lagrange as Lagrange multipliers and the Lagrangian in mechanics, if you've met that, perhaps not. So this is Jean-Louis Lagrange, early 19th century French mathematician. And he did some early work on group theory, although he probably didn't state this theorem quite like this. So what the theorem says is, if you've got finite groups, it's about finite groups, and let H be a subgroup of G, then what? Well, what Lagrange's theorem tells you is something about the order of H in relation to the order of G. Now, when we did cyclic groups, we had a very nice situation, if you can cast your mind back 3 or 4 weeks, which already seems a long time ago. For cyclic groups, we had this fundamental theorem that says for every divisor of the order of G, there is exactly one subgroup of a cyclic group with that order. So, in particular, the order of any subgroup divides the order of the whole group. Now, it turns out that's true for any finite group. The fact that the order of a subgroup divides the order of the group. Okay? The other part, that for each order there's precisely one subgroup, is not true in general. That's true for cyclic groups, it's not true in general. But what is true is that the order of any subgroup divides the order of a group, divides the order of the group. Okay? What Lagrange's theorem doesn't say is that if you've got a factor of the order of the group, then you'll be able to find a subgroup of that order. Now that's not true, and we'll talk about that later on. So this is what Lagrange's theorem says. And we're going to prove that using what's called the Courset decomposition. So essentially what we're going to do is we're going to take our group and we're going to construct, given a subgroup, so there's our subgroup H, we're going to construct a partition of G starting from the subgroup, which I like to think of as giving you a kind of bar of chocolate picture. Each of these parts has the same cardinality as H. So this could be true even if G was infinite, but if G were finite, then each of these parts has the same number of elements as H. So this is a very regular partition of G. And then Lagrange's theorem follows immediately, because each of these parts has the same number of elements. In fact, the same number of elements as H, so the order of H must divide the order of G. So if we were, say, 3 elements in H, and we've got 1, 2, 3, 4, 5 parts, there'd be 15 elements in G, divided equally amongst these 5 parts, so the order of H divides the order of G. So that's going to be our method of proof of Lagrange's theorem. But first we have to construct this partition. So we're going to be using stuff that we did on partitions or equivalently on equivalence relations right at the beginning of semester. So we'll have to remind ourselves about that. And in fact, there are kind of two paths to this bar of chocolate. There's the left-hand path and the right-hand path. And they give you the same answer in the end, but the bars of chocolate you get en route are different. Okay? So I will be a little bit more precise than talking about paths to bars of chocolate. We're going to talk about left cosets and right cosets. In fact, we'll just talk about left cosets because what happens for right cosets is just essentially the same. Okay, so we're going to construct a partition, a very regular partition of G. And the first part of the partition is a subgroup, and then we get these so-called cosets that are the cells of the partition. So that's what we're going to do. So there's a few details to check before we get to Lagrange's theorem. So let's start. So let G be a group. And I'm not going to restrict myself to finite groups yet because I don't need to. So G could be an infinite group. Any of the groups that we've met so far, any group that you haven't met so far. And we need a subgroup. So the data are a group G and a subgroup H. And we're going to define an equivalence relation on G using H. So that's not the best sentence. Perhaps I was better saying using H, we define an equivalence relation on G. And in fact, we could go in two different directions. We could go on the left-hand path or the right-hand path. I'm just going to talk about the left-hand path. So the first thing I'm going to do is define a relation, and then I'm going to check that it is actually an equivalence relation. So for x and y in G, we're going to say that x is related to y. I'll use tilde for the relation. If and only if x inverse y is in H. Okay, so x inverse y is just the product of the group element x inverse with the group element y in the group G. So if we compute this product, it's either in H or it isn't. If it is, then we say that x is related to y. Okay? And what I'm going to do now is check that this is not just any old relation, it's actually an equivalence relation on G. Okay? So we show that tilde is actually not just any old relation, an equivalence relation on G. So we're now just thinking of G as a set, so we can have an equivalence relation on a set. We're going to show that tilde is such a relation. Okay, so can anybody remember what properties a relation has to have if it's an equivalence relation? There's a magic number 3 again. There's always a magic number 3. So which 3 properties does an equivalence relation have to have? Yeah. Symmetric, transitive, and so we've got symmetric beginning with S, transitive beginning with T, missing something beginning with R. reflexive. Good. So we check that tilde is, we usually do them in this order, it doesn't matter which order you do them, reflexive, symmetric and transitive. Notice it is RST if you want a little mnemonic. Reflexive, symmetric and transitive. So we now have to remember what reflexive, symmetric and transitive means. So, reflexive. So we haven't done this kind of thing since the beginning of the semester, which seems like a very long time ago to me. So we're going to take an element in G, and we've got to show that X is related to itself. Well, remember what the relation is. X is related to Y if and only if X inverse Y is in H. So the thing that we're interested in is computing X inverse Y and checking whether or not it's in H. And you can see that if X and Y are the same thing, we're going to get X inverse X, which is the identity, and the identity element is certainly in H because H is a subgroup. So we have X inverse X is the identity, which is in H, since H is a subgroup. We're going to be using the fact H is a subgroup each time. Okay, so X inverse X, which is the combination I'm interested in, that's the identity, and that does indeed live in H. So hence, X is related to itself. Is that okay? What about symmetry? Not symmetric. Now we need to take two elements of our group, in fact just of our set a priori, and we must show that if X is related to Y, then Y is related to X. That's what symmetry means. So there's an implication to show. And here we're going to use another property of H being a subgroup. So I'm going to start with X being related to Y. What does that mean? It means that X inverse Y is in H. That's by definition of tilde. Well, I want to get Y related to X, so I've somehow got to swap these around. I've got to interchange X and Y. So any suggestions as how I might do that? I can use the fact that H is a subgroup. So if this element is in H, which element is automatically in H? An element related to this. Sorry, repeat what is. Well, X. All we know is that X inverse Y is in H. This combination, but there's another element I can immediately write down that's also in H, knowing that this is in H. Yeah, the inverse of this is also in H. Yeah? Because H is a subgroup. So that's another bit of being a subgroup which I'm using. So it's crucial that H is a subgroup, not just any old subset. So if an element is in H, then so is its inverse. But then we can use our computational techniques for computing inverses. So remember, the inverse of a product is the product of the inverses in the opposite direction. So you've known that for matrices for a while, but we discussed that at the beginning of the semester for groups. So the inverse of the product is the product of the inverses, but in the opposite direction. And we also use the fact that comes from uniques of inverses that x inverse all inverse is x. Or if you want, just from the index laws, that -1 times -1 is +1, and x to the 1 is x. Either way. So in fact, we've got y inverse x in H, which is exactly the same as saying that y is related to x. So we started off with x related to y, we assumed that, and from that we've deduced that y is related to x, and that's exactly what symmetry is. So notice we've now used two properties of H being a subgroup. We used the fact that the identity element is in H in the first bit, the reflexivity, and we've used the fact that it contains inverses in the second bit. So you might guess that in the third bit we're going to have to use the fact that it's closed under the binary operation. In fact we do. So transitivity, well, transitive, to be consistent with what I said before. So now we take three elements of the group, and we must show that if x is related to y and y is related to z, then x is related to z. That's what transitive means. Remember, we're kind of using y as a stepping stone to get from x to z. And this is fairly much follow your nose, I think. So I'm going to assume that x is related to y and y is related to z. If you don't want to write this little happy symbol, you could write and if you want to. So x inverse y is in H and y inverse z is in H. That's by definition of the equivalence, definition of the relation tilde. Now I want to get rid of y and just get x and z together. And you can see that this y here is just itching to get its hands on its partner y inverse, so we just multiply this by this. And we can do that, or we can deduce that that product is in H because H is a subgroup. So again, we've used the fact that H is a subgroup. If you've got two elements of H and you multiply them together, you will stay in H because H is closed under the binary operation. So I've multiplied this element by this element and I stay in H. Is that okay? So now I've used all three properties of H being a subgroup, which is quite comforting. Well, I'm not going to do all the steps in the computation. I've got y inverse when I take the brackets away, which gives me the identity element. So I ended up with x inverse z is in H. And that says that x is related to z. Okay, so that shows that my tilde relation is transitive. So hence tilde is transitive. So our conclusion is we've checked reflexivity, symmetry and transitivity. We conclude that tilde is indeed an equivalence relation. On G. So we've got an equivalence relation on G built from the subgroup H. So we can now look at the corresponding partition. Remember, every equivalence relation gives you a partition and conversely. So to compute what the partition is, we need to look at the equivalence classes. Because the equivalence classes are what give you the parts of the partition, the cells of the partition. It tells you which elements live with which other elements. So remember, the equivalence class is constructed as follows. You take an element in your set and you look at all relatives of that element. You put them in a bag. So we're going to take X and we're going to look at all X's relatives. And that's the equivalence class containing X. So then the equivalence class of X is given by, well, our notation that we've used from time to time for the equivalence class is X bar. So X bar is the bag of all X's relatives. So this is going to be a subset of G. So it's a set of all Y in G such that X is related to Y, or Y is related to X. It's the same thing. So it's all X's relatives put in a bag. And we're going to compute what this is. So it's clearly going to be something to do with H, because tilde is defined in terms of H. So that's a set of all Y in G. By the way, this first line is just the definition of X bar. So this first line, the reason is it's a definition of X bar. It's the definition of the equivalence class. But now I'm going to put down what X tilde Y means. It means that X inverse Y is in H. So that's where H enters the story. So that's a set of all Y in G. Well, if X inverse Y is in H, that means that X inverse Y must equal a little h for some little h in big H. Okay? So if X inverse Y is in big H, that means X inverse Y equals a little h for some little h in big H. Okay? X inverse Y is some element of H, in other words, which I'm calling little h. So I want to get Y on its own, because I'm interested in what Y actually is, but I can just get that Y on its own by pre-multiplying this by X. And that's an invertible operation because I can just get back by multiplying by X inverse. So I end up with that. Okay? So on all Y in G that look like X times an element of big H. And this thing is called a left coast. It's called the left coast containing X. So I'll just say that in a second. So let me just write this down again on the top of this page. So I've just written down exactly what I had before at the top of this page. Well, that's the precise description, but we always have a slightly sloppy description as well. Y is x times h for some little h in big H. So what x bar is, it's the collection of all elements that look like x times some element of big H. And the notation that we use, so this is a definition of notation. Well, it's quite a sensible notation. It's x times big H. So x times big H means the set of all x times little h as h runs through big H. So you multiply all elements of big H on the left by x, and that gives you a subset of G. And this is called the left coset of H in G that contains X. It's called the left coset. Well, it's the left coset because the X is on the left. You could say, well, why isn't it the right coset because H is on the right? It's just a matter of convention. Okay, so the left coset has X on the left. Now, as I said, there's also a right-hand path where we look at a slightly different equivalence relation, and we end up with X on the right, and that's called the right coset. But the theory for left cosets mirrors the theory for right cosets. So we're actually just looking at the theory for left coset. Okay, so this is a left coset. It's a set of all elements of G that look like X times some element of H. So we need to do an example of computing these in a second, but let me just draw a picture, which is in fact the bar of chocolate picture I drew originally. What we know now then